Imagine, if you dare, a world, not unlike our own, but fundamentally, startlingly different. A world where the truth wasn't a discovery, it was an inheritance. You were born into it, you lived by it, and you died believing it. This wasn't merely a matter of faith. It was the very framework of understanding, laid down by venerable sages of antiquity and reinforced by generations of unwavering belief. This was a universe where the earth stood utterly still, the undisputed sovereign at the very heart of creation. Around us, perfect, crystalline spheres revolved, carrying the sun, moon, and stars in an eternal, flawless dance. Every celestial body, every natural phenomenon, from the changing seasons to the ebb and flow of tides, was seen as a divine testament, a fixed, unchanging design. Knowledge wasn't forged in the fires of observation or the crucibles of experimentation. It was unearthed from dusty, revered ancient texts, from the pronouncements of Greek philosophers like Aristotle and Ptolemy, and the infallible doctrines of theologians. To challenge these established truths was not merely an intellectual disagreement. It was an act of profound heresy, a questioning of the very divine order itself. This was the intellectual landscape of the 15th century, an era utterly dominated by scholasticism, a grand, intricate tapestry of medieval philosophy that meticulously stitched together reason and faith. Aristotle and Ptolemy weren't just thinkers. They were the unchallenged oracles of science, their every word etched into stone, their ideas meticulously copied and recopied through centuries of manuscripts, were unshakable, the very bedrock of understanding. Their elaborate system, while a marvel of intricate logic, had become a rigid intellectual cage, leaving little room for new inquiry or contradictory evidence. But here's the secret. Beneath that seemingly unyielding surface, something restless, something dangerous, was beginning to stir. The Renaissance, that explosion of art and humanism, hadn't it just revived a thirst for classical beauty? It had rekindled a far more subversive flame, individual curiosity, the burning desire to question, to critically examine. Scholars, once content to merely interpret ancient wisdom, now yearned to go beyond it. Suddenly, minds weren't just admiring old knowledge. They were wanting to create new knowledge, to forge their own paths into the unknown. Then came the oceanic seismic shifts, the great voyages of exploration. Think Columbus, think Magellan, think the very edges of the known world being pushed into oblivion. These weren't just journeys, they were intellectual earthquakes. Old geographical notions, maps, and long-held beliefs about the world's size and shape were utterly shattered. For centuries, cartographers had relied on Ptolemy's geography, but explorers returned with tales of vast new continents and circumnavigations that proved old maps were simply wrong. Imagine being told the Earth was flat, only for ships to return from sailing around it. This wasn't just a discovery of new lands. It was a discovery of just how much we didn't know. It cracked open the intellectual universe, revealing a world far grander and more complex than previously conceived. And then, the ultimate game changer, the invention of Gutenberg's printing press around 1440. This wasn't just a machine, it was a revolution in itself. Before, books were rare, expensive, painstakingly hand-copied, accessible only to a select few. Knowledge was a guarded treasure, confined to monasteries and the elite. Now, suddenly, ideas weren't just whispered. They could explode across continents like wildfire. The cost of books plummeted, literacy rates slowly climbed. and information once jealously guarded in monasteries and elite circles began to democratize. And here's the kicker. When you started printing old texts en masse, comparing copies, discrepancies, and outright errors became glaringly obvious. The infallible authorities started to look, well, fallible. The cracks in the ancient edifice of knowledge were becoming impossible to ignore. Questions, once mere whispers in the dark corners of libraries, began to shout. What if what we'd always believed wasn't just incomplete, but fundamentally wrong? What if the universe wasn't just bigger, but infinitely stranger, more complex, more marvelous than our wildest dreams? The comfortable certainties of the past were crumbling, replaced by a thrilling, terrifying sense of intellectual vertigo. This, my friends, is the incandescent story of a revolution, not one forged in the heat of battle with blood and gunpowder, but one ignited in the quiet laboratories of the mind by sharp intellects and daring gazes. A revolution silent in its execution, yet absolutely deafening in its world-shattering consequences. This is the scientific revolution, a blazing period roughly spanning the 16th to the 18th century. It's when humanity collectively decided, enough reading the ancient script. It's time to pick up the pen and write the book of nature ourselves. It was a profound shift. Faith didn't vanish, no. But reason and relentless observation rose to stand proudly alongside revealed truth, demanding their place at the table of knowledge. This was a paradigm shift, a colossal intellectual earthquake that quite literally pulled us from the shadows of unquestioning belief and propelled us into the glorious, dazzling light of empirical knowledge. Prepare yourselves, because the very dawn of modern science is about to explode into being. We're not just observing history, we're witnessing the birth of the scientific method itself. The era of passive acceptance was over. The age of active inquiry had begun. Our thrilling saga dives deeper into the celestial sphere, beginning with one man whose quiet calculations would ignite a cosmic firestorm. A Polish cleric by day, an amateur astronomer by night, he meticulously observed the night sky, day after day, year after year, with a growing sense of unease. The heavens, according to the ancient model, were supposed to be perfect, but his observations didn't quite fit the tidy, established framework. His name, Nicholas Copernicus, born in 1473. The astronomy of his time, the Ptolemaic model, was a bewildering, convoluted mess. Imagine a Rube Goldberg machine of celestial mechanics, a chaotic dance of epicycles and deferents, circles upon circles, all just to force the planet's erratic movements into the impossible framework of an immobile Earth at the center. It was cumbersome, inelegant, and frankly, a bit ridiculous. Planets would sometimes appear to move backward in their orbits, a phenomenon called retrograde motion, which Ptolemy's model explained with these elaborate nested circles. Copernicus, driven by an almost aesthetic sense of simplicity, a belief that God's universe should be orderly and beautiful, thought, there has to be a simpler, more beautiful, more elegant way for God's universe to operate. He saw the system not just as wrong, but as artistically flawed. After decades of secret, painstaking work, and almost posthumously fearing ridicule and controversy, his magnum opus was finally published in 1543, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. This wasn't just a book, it was a cosmic manifesto. In it, he dared to propose a revolutionary, mind-bending idea. The sun, not the earth, was the true center of the universe. A new, modern, and gloriously heliocentric model was unveiled, a radical departure from millennia of accepted truth. Imagine the sheer audacity. He didn't just shift planets. He displaced humanity from its comfortable divine perch at the cosmos' center. This wasn't immediately embraced. Oh no. It was an intellectual earthquake, its aftershocks reverberating for centuries, forcing humanity to redefine its place in creation. It was a seed planted in tumultuous ground that would take generations to fully germinate, but it would forever, irrevocably change our perception of our place in the vast cosmic tapestry. The universe, once intimately centered around us, suddenly became a far vaster, more indifferent place. But the cosmos wouldn't reveal its secrets so easily. Next on our cosmic stage is the truly enigmatic Tycho Brahe. This isn't your average astronomer. He was an eccentric Danish nobleman with a wild beard, a legendary temperament, and yes, a replacement nose made of gold and silver after a duel. Born into privilege, Tycho convinced the Danish king to grant him an entire island, Hven, where he built the most advanced astronomical observatory of his time in the 16th century, complete with gigantic quadrants and armillary spheres, an entire island dedicated to observing the heavens. Tycho, surprisingly, didn't fully believe in Copernicus's heliocentrism, proposing his own geoheliocentric model where the planets orbited the sun, but the sun still orbited a stationary Earth. However, his obsession was an almost maniacal pursuit of precision. For decades, armed with gigantic custom-built instruments, he meticulously collected the most detailed, scrupulously accurate astronomical data ever seen, all with the naked eye. He charted the positions of stars and planets night after night, compiling a cosmic treasure trove of information that would prove invaluable. He died in 1601. His colossal data sets, a treasure trove of cosmic measurements, were destined for one man. A young, brilliant, and equally driven German mathematician named Johannes Kepler. Tycho's intellectual heir, Kepler, obsessed over the Martian data, a planet whose erratic dance had stumped everyone. The precision of Tycho's observations meant that previous models, even Copernicus's, simply couldn't account for Mars's movements. Months turned into years of relentless, agonizing calculations. He tried fitting the data to every conceivable combination of perfect circles, but it simply didn't add up. The perfect circles, the ancient belief in celestial perfection, kept breaking. Kepler, a mystic who believed in the harmony of numbers, was initially resistant to abandoning the circle, the perfect shape. And then the epiphany, a blinding flash of insight after years of struggle. The orbits weren't perfect circles as both the Greeks and Copernicus had believed. They were ellipses. This simple yet revolutionary insight shattered a 2,000-year-old dogma. In 1609 and 1619, Kepler published his 3 laws of planetary motion, describing with stunning mathematical elegance exactly how planets truly move around the sun. A genius, a mystic who saw divine harmony in numbers, a relentless mathematician, Kepler unveiled the true, elegant dance of the cosmos, laying the precise mathematical groundwork for the next monumental giant. But for the scientific revolution to truly explode, proposing grand ideas wasn't enough. We needed more than theory. We needed to observe the universe directly and, crucially, to experiment with it. And for that, no one was more crucial, more revolutionary than Galileo Galilei. Rightfully dubbed the father of modern science, a man of fiery intellect and a famously quarrelsome nature, yet utterly passionate about mathematics and physics. His keen mind applied mathematics not just to the heavens, but to the mechanics of the terrestrial world, bridging the gap between heavenly and earthly phenomena. Galileo didn't invent the telescope, but in 1609 he seized the rudimentary design, dramatically improved its magnification and clarity, and, in a stroke of genius, instead of pointing it at distant ships in the harbor, he did something utterly unprecedented. For the first time in history, he aimed it at the sky. What he saw was nothing short of astounding, a cosmic revelation that shattered millennia of dogma. He saw Jupiter's moons orbiting Jupiter itself, not Earth, a miniature solar system proving not everything revolved around us. This directly contradicted the Aristotelian idea that all celestial bodies must orbit the Earth. He observed the phases of Venus just like our moons, undeniable proof of the heliocentric model, as only a planet orbiting the Sun inside Earth's orbit could display such a full range of phases. He saw mountains and craters on the moon, proving it wasn't a perfect, unblemished sphere, thus challenging the ancient belief in celestial perfection. He even spotted sunspots, revealing the sun itself wasn't perfect, further dismantling the notion of immutable, flawless heavenly bodies. In 1610, he rushed to publish his groundbreaking observations in Sidereus Nuncius, the Sidereal Messenger, a slim volume that sent shockwaves through the intellectual world. His discoveries weren't just new facts. They were an intellectual battering ram, systematically destroying the immutable perfection of the Aristotelian heavens. But Galileo wasn't just a stargazer, he was an experimenter. His meticulous studies on falling bodies, demonstrating that objects fall at the same rate regardless of their mass, ignoring air resistance, revolutionized the understanding of motion. His work on the pendulum, revealing its consistent swing, laid the groundwork for precise timekeeping, and his principle of inertia, stating that an object in motion stays in motion unless acted upon by an external force, laid the fundamental groundwork for classical physics, revealing how things move here on Earth. He brought the spirit of repeatable, verifiable experiment to the forefront of scientific inquiry. Yet, such revolutionary vision rarely arrives without intense friction. Galileo's unwavering, almost defiant embrace of a sun-centric cosmos placed him on a direct collision course with the unyielding doctrines of the Church, a formidable power deeply unwilling to surrender its perceived central authority, both earthly and cosmic. The Church viewed the heliocentric model as directly contradicting literal interpretations of Scripture, and more importantly, as a dangerous precedent that could undermine its spiritual and intellectual authority. The fateful year of 1633 saw him stand before the Holy Inquisition, a moment etched into history. His scientific truth was forced to bend under duress, and he would spend his remaining years under house arrest, his grand insights silenced, at least publicly, a tragic personal cost for groundbreaking knowledge. But even cloistered, a new dawn had broken. The universe, seen through his telescope, was irrevocably changed, its ancient mysteries giving way to a grander, more dynamic reality. Despite the persecution, the seed of true empirical observation had been firmly planted. The study of the cosmos and the very pursuit of scientific ideas would never, ever be the same. The scientific revolution, we realize, wasn't merely about gazing at the stars. It was equally, perhaps even more profoundly, about Earth, about matter, about the very foundations of how we know what we know. The celestial breakthroughs demanded a new way of thinking about all knowledge. For this immense task, humanity needed more than just improved instruments. We desperately needed new methods of thinking. Enter Francis Bacon, 1561 to 1626, an English philosopher and statesman, a brilliant legal mind who, though not a scientist in the lab coat sense, was a true prophet of this burgeoning age of new knowledge. He articulated the philosophical underpinnings for how science should be done. His most pivotal work, Novum Organum, the New Organ, published in 1620, was a direct, scathing criticism of the ancient Aristotelian method of pure deduction, reasoning from broad principles without direct observation. Bacon argued that this old way of thinking, based on what he called idols of the mind, such as prejudices and faulty generalizations, hindered true understanding. Bacon didn't just critique, he proposed a revolutionary new path, the inductive method. Instead of starting with grand theories and trying to make observations fit them, you start with the ground up, meticulous, detailed observation. You collect data, you perform controlled experiments, you repeat them, you gather overwhelming evidence. And only then do you formulate general conclusions. This was the blueprint for systematic experimentation, for embracing trial and error, for diligently accumulating empirical evidence. He envisioned a collaborative scientific endeavor, a vast network of researchers collecting data to build a comprehensive understanding of nature. His famous adage, "knowledge is power," wasn't just a clever phrase. It was a rallying cry. It implied that true power lay not in inherited wisdom, but in the ability to manipulate and understand nature by discovering its underlying laws. Now, another brilliant mind was forging his own intellectual weapon. René Descartes, 1596 to 1650. His journey began with radical doubt, questioning everything he thought he knew until he found one undeniable truth. I think, therefore I am. His famous cogito ergo sum. This profound search for certainty through methodical doubt laid the very bedrock of rationalism, the powerful idea that reason itself is the primary, most reliable source of knowledge. Descartes sought to build knowledge from irrefutable, self-evident truths, much like constructing a geometrical proof. And what an elegant tool he bequeathed us, analytic geometry. Imagine taking two seemingly separate mathematical worlds, the abstract power of algebra and the visual beauty of geometry, and merging them into one seamless system. Suddenly, curves, lines, and shapes, previously just visual figures, could be described with precise equations. This wasn't just a mathematical trick. It was a transformative lens through which to view reality. It provided a universal language for describing motion, shapes, and positions, which would be crucial for future physicists. The universe, once an intangible mystery, could now be mapped, measured, and understood with the undeniable precision of mathematics. For Descartes, the entire cosmos was a giant clock, an intricate, perfectly designed machine operating according to discoverable mathematical laws. This powerful mechanistic view wasn't cold or clinical. It was liberating. It stripped nature of its ancient, unpredictable mysticism and gave us permission to disassemble it piece by piece through rational inquiry to truly understand its workings. So, While Bacon taught us how to ask the world questions through experiments, Descartes equipped us to comprehend its answers through pure, rigorous logic. Together, they orchestrated a grand symphony of observation and reason, creating the most powerful intellectual weapons the human mind had ever wielded for unveiling every hidden secret. The intertwining of empirical observation and rational deduction became the hallmark of the new science. And it wasn't just the grand cosmos opening up. New disciplines on Earth were taking thrilling shape. Anatomy, for instance, had been shackled by over 1,000 years of uncorrected errors, relying on ancient texts rather than direct observation. For centuries, medical knowledge was based on the writings of Galen, a Roman physician from the 2nd century, who had often dissected animals, not humans, leading to persistent inaccuracies. Then came Andreas Vesalius, a true titan who, in 1543, broke centuries of taboo. With the audacious eye of an artist and the unflinching precision of a surgeon, he began dissecting the human body like never before. He risked social ostracism and even legal trouble to gain first-hand knowledge. His monumental work, De Humani Corporis Fabrica, wasn't just a book. It was a revolution in itself. It was so detailed, so accurate, with exquisite illustrations, that it revealed the sheer wonder and astonishing complexity of our own flesh, correcting anatomical mistakes that had persisted since ancient Rome. The veil over our physical selves, our very being, was finally torn away. Beyond the human body, the very essence of matter was being interrogated. Chemistry began its painstaking, systematic divorce from the mystical arts of alchemy. Alchemists had pursued elusive goals like turning lead into gold or discovering the elixir of life, often relying on arcane rituals and secret formulas. But now, figures like Robert Boyle, 1627 to 1691, often called the father of modern chemistry, moved past turning lead into gold. He emphasized rigorous experimentation and the systematic study of the properties of matter. In 1662, he enunciated his famous law on gases, demonstrating a scientific approach to understanding matter, studying the relationship between pressure and volume. He also proposed the concept of elements as unchangeable particles, laying crucial groundwork for future chemical understanding. And then, the incredible world of the unseen was revealed. Microscopy, pioneered by figures like Antony van Leeuwenhoek, 1632 to 1723. In the late 17th century, he meticulously ground lenses, achieving magnifications previously unimaginable, peering into drops of pond water and human blood, discovering an entire invisible universe of animalcules, microorganisms. He was the first to see bacteria, spermatozoa, and blood cells, describing them with astonishing accuracy. This wasn't just a curiosity. It was a shocking revelation that opened the door to modern biology, showing life existed on a scale previously unimaginable. The world was suddenly far more populated, far more vibrant than anyone had ever conceived. The scientific revolution, then, was truly universal. It was no longer just about studying the grand, distant heavens. It was about everything. Every corner of the universe, from the majestic sweep of the stars to the hidden wonders of the tiniest, unseen beings, was now waiting patiently to be unveiled by the relentless power of the new scientific method. It was a testament to the insatiable human desire to explore, to dissect, and to understand. And so, we arrive at the breathtaking climax of this intellectual revolution. The stage is set for a mind so extraordinary, so profound, that it would synthesize all the scattered threads of scientific discovery, weaving them into a singular, magnificent tapestry of harmony and precision. A work that would not just define physics for centuries, but shape our very understanding of reality. His name, Isaac Newton. Born the very same year Galileo died, almost as if destiny itself was passing the torch, Newton was a force of nature, a polymath of unparalleled genius. Mathematician, physicist, astronomer, alchemist, theologian. He was a mind that seemed to absorb and transform all knowledge. He was a solitary figure, often difficult, but possessed of an intellect that could delve into the deepest mysteries of the universe. As he himself humbly put it, "If I have seen further than others, it is by standing upon the shoulders of giants." His insights were built on the meticulous observations of Brahe, the elegant laws of Kepler, and the empirical foundations laid by Galileo. His crowning achievement, his monumental masterpiece, was the Philosophiae Naturalis Principia Mathematica, published in 1687. This wasn't just a book. It was quite possibly one of the single most influential scientific works in all of human history. Within its pages, Newton didn't just present theories. He demonstrated them with unassailable mathematical rigor. He meticulously formulated his 3 laws of motion, which describe how everything from a thrown ball to a galloping horse behaves, from the smallest pebble to the grandest planet. These laws, inertia, force equals mass times acceleration, and action-reaction, provided a universal framework for understanding how objects move and interact. But then, with breathtaking elegance, he unveiled the law of universal gravitation. Imagine this. For the very first time, it was mathematically proven that the identical, invisible force that pulled an apple from a tree to the ground was the same force that kept the moon in its perpetual orbit around the Earth, and kept every colossal planet locked in its graceful dance around the sun. This was the ultimate unification, explaining both terrestrial and celestial mechanics with a single, elegant principle. The universe, in all its immense scale, was governed by the same exact mathematical laws. Newton provided nothing less than a complete, unified, and utterly brilliant mathematical description of the entire universe. He invented calculus, a new mathematical language, specifically to articulate these relationships, allowing for the precise prediction of planetary movements and the trajectories of projectiles. The fragmented cosmos that Copernicus, Kepler, and Galileo had begun to reveal now clicked into place, unified by a single, elegant equation. Descartes' mechanistic vision found its ultimate, perfect expression. The universe was no longer just a giant clock. Newton had not only identified its ticking mechanism, but he had given us its comprehensive instruction manual. This was the ultimate triumph of human reason, demonstrating that the universe was not chaotic, but orderly and comprehensible. Newton's impact was, quite simply, incalculable. Newtonian physics became the undisputed paradigm for all of science, the gold standard, the model for every other discipline to emulate. His work fostered an immense confidence in human reason and direct observation that didn't just grow, it absolutely soared to unprecedented heights. The world, once mysterious and unpredictable, was now seen as a machine operating under discoverable laws, inspiring thinkers across all fields. This burgeoning confidence wasn't confined to lone geniuses. The 17th and 18th centuries saw the explosion of scientific societies, the very birth of the modern scientific community. Think of the prestigious Royal Society of London, founded in 1660, and the Académie des Sciences in Paris, founded in 1666. These weren't just clubs. They were the new temples of knowledge, vibrant hubs where the brightest minds could gather, share their discoveries, engage in rigorous debate, and collaborate on grand projects. They published journals, standardized experimental procedures, and fostered a culture of critical review. Crucially, they moved scientific inquiry away from individual patronage or ecclesiastical control, fostering a spirit of open inquiry and peer review. No longer did a new discovery languish in a private manuscript. It was presented, scrutinized, and either accepted or rejected by a community of peers. The scientific revolution, then, was far more than just a collection of new facts. It fundamentally reshaped our very way of thinking. It taught us to ask not just why, which often led to mystical or divine explanations, but definitively how. It showed us the overwhelming, irrefutable power of empirical evidence, rigorous reason, unyielding logic, and systematic experimentation. It taught us a profound, liberating lesson: to question, even to distrust, blind authority, and to relentlessly seek truth for ourselves. Through direct observation of the world and the beautiful, elegant formulation of mathematical laws that govern it, the universe was no longer to be interpreted, but investigated. And so, the scientific revolution didn't simply end at a specific moment. Its powerful, transformative ripple effects spread outwards, expanding through the 18th and 19th centuries, reshaping everything in their path. Its principles became the bedrock for understanding and progress across all spheres of human endeavor. These ripples directly gave rise to the Enlightenment, that colossal intellectual movement that, inspired by the breathtaking success of science, boldly applied the principles of reason, empiricism, and critical thinking not only to nature, but to society itself, to politics, to economics, to human rights. Thinkers like John Locke, Voltaire, and Montesquieu, electrified by the triumphs of scientific inquiry, championed radical ideas: liberty, tolerance, individual rights, and the revolutionary concept of the separation of powers. They argued that just as the natural world operated by discernible laws, so too should human societies be governed by rational principles, rather than by arbitrary authority or inherited privilege. The very same reason that had so brilliantly unveiled the universal laws of the cosmos now desperately sought to unveil the laws of a truly just and equitable society. The philosophes of the Enlightenment envisioned a world reformed by rational thought, free from the shackles of superstition and tyranny. These profound ideas, born from the crucible of scientific thought and the Enlightenment, were the very fuel, the explosive energy, for the grand political revolutions of the 18th century. Think of the American Revolution, 1776, and the earth-shattering French Revolution, 1789. The principles of reason, self-determination, and individual liberty forged in the scientific crucible resonated deeply in the ringing declarations of rights and the passionate pursuit of representative governments around the globe. The belief that truth could be discovered through reason and evidence, not just decreed, directly challenged the divine right of kings and the old aristocratic order. And the impact didn't stop there. The scientific revolution was, without a doubt, the direct mother of the Industrial Revolution. Consider this: without a fundamental understanding of physics, of pressure, temperature, energy. The steam engine, that icon of industrial power, would have been impossible. James Watt's improvements to the steam engine, for example, were rooted in scientific understanding of thermodynamics. Without advances in chemistry and material science, the factories that powered a new age simply couldn't have existed, unable to process raw materials or produce the necessary machinery. This was the application of scientific understanding directly transforming technology, utterly reshaping the global economy, urbanizing populations, and creating the very fabric of the modern world we inhabit today. It changed how we work, where we live, and how we interact with our environment, ushering in an era of unprecedented technological innovation and economic growth. What made this era so utterly unique, so intensely fascinating, so captivating? It was the astonishing courage of a few brave individuals who dared to challenge millennia-old dogmas, risking everything for truth. It was the breathtaking beauty of discovering a universe not of chaos, but of elegant, understandable laws, a cosmos singing with mathematical harmony. It was the profound humility of accepting that knowledge isn't a fixed destination, but an endless, exhilarating journey. Above all, it was the unwavering trust in humanity's innate, extraordinary ability to observe, to measure, to reason, and most powerfully, to question everything.